Multiplication theorem for independent events. The theorem states that if two events A and B are independent, then the probability of the occurrence of both of them, A and B, is the product of individual probabilities of A and B. Symbolically, probability of happening of both the events is probability of A and B, or probability of A intersection B is equal to probability of A multiplied by probability of B. This theorem can be extended to three or more independent events. For three events A, B, C, probability of A, B and C, or probability of A intersection B intersection C is equal to probability of A multiplied by probability of B multiplied by probability of C. For example, in two tosses of a fair coin, what are the chances of head in both? When we toss a coin two times, or if two coins are tossed at a time, the possible outcomes are 4. Probability of head in first toss is 1 by 2 and probability of head in the second toss is 1 by 2. Probability of head in both tosses is 1 by 2 into 1 by 2 equal to 1 by 4. How to calculate probability in case of dependent events? Different situations are given in this column and respective formulas are given in this column. Probability of occurrence of at least A or B when events are mutually exclusive. Probability of A union B equal to probability of A plus probability of B. When events are not mutually exclusive, then probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. Probability of occurrence of both A and B. Probability of A intersection B is equal to probability of A plus probability of B minus probability of A union B. We can obtain this result from this equation. Probability of A intersection B on left hand side and probability of A union B on right hand side. Probability of occurrence of A and not B. Not B means B complement. Probability of A intersection B complement is equal to probability of A into probability of A intersection B. Probability of occurrence of B and not A. Probability of A complement intersection B is equal to probability of B multiplied by probability of A intersection B. Probability of non-occurrence of both A and B. Non-occurrence of A and B indicates A complement and B complement. So probability of A complement intersection B complement is equal to 1 minus probability of A union B. Probability of non-occurrence of at least A or B. Probability of A complement union B complement equal to 1 minus probability of A intersection B. How to calculate probability in case of independent events? Probability of occurrence of both A and B, probability of A intersection B equal to probability of A multiplied by probability of B. Probability of non-occurrence of both A and B, probability of A complement intersection B complement is equal to probability of A complement multiplied by probability of B complement. Probability of occurrence of A and not B, probability of A intersection B complement equal to probability of A multiplied by probability of B complement. Probability of occurrence of B and not A is equal to probability of A complement intersection B is equal to probability of A complement multiplied by probability of B. Probability of occurrence of at least one event, probability of A union B is equal to probability 1 minus probability of A complement intersection B complement is equal to 1 minus probability of A complement multiplied by probability of B complement. Probability of non-occurrence of at least one event, probability of A complement union B complement equal to 1 minus probability of A intersection B, where probability of A intersection B equal to probability of A into probability of B. So we subtract product of these two probabilities from 1. Probability of occurrence of only one event. Probability of A intersection B complement plus probability of A complement intersection B is equal to probability of A into probability of B complement from first bracket plus probability of A complement multiplied by probability of B from the second bracket. Problem. An inspector of the Alaska pipeline has the task of comparing the reliability of two pumping stations. Each station is susceptible to two kinds of failure, pump failure and leakage. When either or both occur, the station must be shut down. The data at hand indicate that the following probabilities prevail. At station 1, probability of pump failure is 0.07 and probability of leakage is 0.10. Probability of both is 0. At station 2, probability of pump failure is 0.09 and probability of leakage is 0.12 and probability of both pump failure and leakage is 0.06. Which station has the higher probability of being shut down? Solution. We are given probability of failure or leakage, which is equal to probability of pump failure plus probability of leakage failure minus probability of pump failure intersection leakage failure. We have to find this probability. For station 1, probability of pump failure is 0.07 plus probability of leakage failure is 0.10 minus probability of pump failure intersection leakage failure is 0. Solving these probabilities, we get 0.17. So 0.17 is the probability of pump failure or leakage failure. And at station 2, probability of pump failure is 0.09 and probability of leakage failure is 0.12. Probability of pump failure intersection leakage failure is 0.06. Solving these probabilities, we get 0.15. Thus, station 1 has the higher probability of being shut down. Example number 1. A card is drawn from an ordinary deck of 52 playing cards. What is the probability that the card will be either a king or a jack? We know that there are 52 playing cards and we have to draw one card and we have to find the probability that the card will be either a king or a jack. Let A denotes the event king and B denotes the event jack. These are mutually exclusive events as both cannot occur at a time. Thus we use addition law of mutually exclusive events. Probability of A or B is equal to probability of A union B equal to probability of A plus probability of B. Now total possible outcomes in the sample space S are 52C1. Out of 52 playing cards, any one of the card can be selected, so we use the rule of combinations. 52C1 equal to 52. You can solve the combinations by using the calculators. Let A denotes card as king and let B denote card as jack. Since we know that there are 4 kings in a deck of 52 playing cards, so favorable outcomes to the event A are 4C1. Any one of the king can be selected. Possible ways are 4. Probability of event A is equal to number of favorable outcomes to the event A divided by total possible outcomes, which is equal to 4 over 52 and is equal to 1 by 13. Since B denotes card as jack, favorable cases to B are 4C1s because there are 4 jacks in 52 playing cards. Any one of the jack can be selected, so 4C1 ways are there which are favorable to the outcome B to the event B. Probability of B is equal to favorable outcomes to the event B divided by total possible outcomes, which is equal to 4 over 52. Simplifying this, we get 1 by 13. Therefore, probability of A or B is equal to probability of A plus probability of B, because these two, A and B, are mutually exclusive events which cannot occur together. So probability of A is 1 by 13, and we found probability of B 1 by 13. Adding these two probabilities, we get 2 by 13, which is the probability of a card will be either a king or a jack. Example number 2. A pair of fair dice is rolled once. Find the probability that the sum of the upper dots is either 6 or 9. Now you are familiar with constructing the sample space when a pair of fair dice is rolled once. We know that number of sampling points in the sample space when a pair of dice is rolled is 6 raised to power n equal to 6 power 2 equal to 36. There are 36 possible outcomes in the sample space. Let A denote sum of dots is 6 and let B denote sum of dots is 9. These are mutually exclusive events because they cannot occur together. Hence we use addition theorem for mutually exclusive events. The sum is 6. We can get the sum 6 by the outcomes 5, 1, 4, 2, 3, 3, 2, 4 and 1, 5. And we can get the sum 9 by the outcomes 3, 6, 4, 5, 5, 4 and 6, 3. So A equal to 1, 5, 2, 4, 3, 3, 4, 2 and 5, 1. The sum is 6. Number of favorable outcomes are 5 in this set. Probability of A equal to favorable outcomes over total possible outcomes, which is equal to 5 over total outcomes 36. Since B denotes the sum is 9, the sum 9 is with the events 3, 6, with the outcomes 3, 6, 4, 5, 5, 4 and 6, 3. So favorable outcomes are 4. Probability of B is number of favorable outcomes to the event B divided by total possible outcomes in the sample space, 4, which is equal to 4 over 36. Therefore, probability of A or B is equal to probability of A plus probability of B, which is equal to 5 over 36 plus 4 over 36 is equal to 9 by 36 equal to 1 by 4. Example number 3. A fair die is rolled once. What is the chance that either an even number or a number greater than 3 will turn up? Let A be an even number occur and let B denotes a number greater than 3 occurs. These events are not mutually exclusive events because A may happen, B may happen, or both A and B happen. So we use addition law of not mutually exclusive events. Probability of A or B is equal to probability of A plus probability of B minus probability of A intersection B. Here a die is rolled only once, so number of sampling points in the sample space are 6. Sample space will consist of 1 dot, 2 dots, 3, 4, 5 and 6 dots. Let A denotes an even number occurs, then A consists of 2, 4 and 6. Number of sampling points in A are 3. Probability of A is number of favorable outcomes to the event A divided by total possible outcomes, which is 3 by 6. Let B denote the number greater than 3. B equal to 4, 5 and 6 and number of sampling points in B are 3. Probability of B is 3 by 6. A intersection B is A set intersection B set, which is 4 and 6. Number of sampling points in A intersection B is equal to 2. So number of favorable outcomes in the set A intersection B divided by total possible outcomes is 2 by 6. Now we use the formula probability of A or B, which is equal to probability of A plus probability of B minus probability of A intersection B. Using these probabilities we get 2 by 3.